Hey, welcome back to our Lab 9, Week 9 of Graduate Statistics at UC. So, we have just run our first follow-up test to help our imaginary cousin figure out what to do in terms of major. So this first one that we ran was the LSD. And again, I want to go over this base code because that's what you need to use if you want to run an LSD as a follow-up. So the first step is to rerun your ANOVA model, okay? The second step is to run this function, lsd.test. And what you do, you pass as first input the model, right? Whatever you named it. In this case, we named it lm.model. Second thing, this parameter TRT, you identify your explanatory variable whose levels you want to compare. Here you have to tell R what the degrees of freedom of the error is, and that is 47 you get in your ANOVA table. Remember, the residuals are the error, what variance is left over and unexplained, that's your error, and that's 47 degrees of freedom. And then you need the MS error, which you get from the ANOVA table. That's really just the only difference between this and the t-test, is that it uses this mean square error, but not of the major category, of the error. Remember, we're using this for the denominator. Alpha, because we're running the LSD, we say that we want no correction, because remember, the only protection we're putting in is the fact that we're using this MS error instead of using the error as is typically computed by the t-test. This tends to be a little larger. And then we're setting up group as false. And by setting up grouping as false, we're asking R not to group the output. And I'll show you what happens if we set this to true. And we set console to true because this is us asking R to actually show us the output. So when we ran this, we saw, this is a long table. It gives us the mean for each one of the conditions, for each one of the groups, the standard deviation. It gives us the number of majors in each one of them. It gives us the confidence interval, the lower limit and the upper limit for each one of them. It also gives us the minimum and the maximum of each one of them. It gives us the mean difference, it gives us the p-value, and it gives us the whether the difference is significant or not at the 0.05 level, which we told R is what we wanted to use. So there are just two differences. Now, if we say that group is true, what R does, here's what me trying to explain it, and then we're going to see it in the output. When you say, you typically want it set to keep the console true, and then so that the output is presented, and the group argument controls how the output is presented. If we set it to true, the output groups the treatment means into subsets where treatments with the same letter are not significantly different from one another. For example, if R groups two factors and call them A, they're not significantly different from each other. And then if groups them as Bs, they're not significantly different from each other. But A's and B's are different from each other. It's very hard to explain in words, but if we turn this to true and run, you see what it is. The results are the same, but looked at, it put engineering, labeled engineering A, and it labeled computers and physical sciences as B. So it grouped these two. This means that computers and physical science is not different from each other because they both have Bs. And engineering is different from computer science, statistically different because A and B is different. And engineering is different from physical science because A and B is different. I just find this a little bit confusing, so I prefer to just leave group fixed in F. It has like the simplest output that you can quickly look, get the p-value, get the confidence intervals, all in there, all that you need. Now, we said that LSD is only appropriate when you're doing confirmatory testing with 3 or less comparisons. Here, we would be fine using LSD because we're doing confirmatory testing. We actually, given our question, we actually want to compare all of those. Now, if you were under a circumstance where the comparisons were more exploratory, you just want to compare everything to everything, just because you want to explore. In that case, you would use Bonferroni correction if you don't have that many comparisons. So in this case, if we were being more exploratory in our comparisons, there was not like a particular reason for making each one of the comparisons, which we do have, because our imaginary cousin has 2 constraints. She has the preference and she has the salary. So she wants to know all of the comparisons so she can make the most informed decision. But if not, we could use LSD still, but with Bonferroni correction. So in that case, you use the exact same code, everything the same. The only thing that differs is that here, instead of putting no correction, in terms of P adjustments, no adjustment, none, is what we did before. Here we're telling it use Bonferroni correction, which means it will multiply the p-value by the number of comparisons. That's how it's adjusting the p-value. So if we run here, even with the correction, we still have computers and engineering different, engineering and physical science different, and computers and physical science not different. So the differences between engineering and computer science and physical science and engineering is large enough and reliable enough that even after corrections, it's still significant. If you do too many corrections, what may end up happening is that you start increasing the p so much that it then crosses the boundary and is no longer significant. So you should just use it if there is a reason to make such stringent correction. The happy medium, as we talked about in class, is Tukey's HSD. So as I said in the lecture video, this allows for more correction than the LSD, but less stringent than Bonferroni. You can read this is exactly what I said in class as well. So I'm not going to read it over here again. So how do you run it? Pretty much in the same way as before, but instead of using the function lsd.test, we do the honest significant difference test, which is another name for the Tukey's test. Input the model name, major category again. Then I still would do root F and console T. So that's all we need for this one. And then we run it. And all you need here is to look at the differences in the same way as before. And again, it's consistent, regardless of how we're doing this time, because there's such few number of comparisons, and they're, the differences are large enough that they're really at the extremes of the tails. So even if we correct, we continue to see the same results over and over again. All right. So these are the 3 possibilities in how to run it. So we can make our final decision and interpretation. So let's do that. Our decision. The one-way ANOVA supported the decision to reject the null hypothesis that the median salary was equal across the 3 major categories under analysis. Post hoc analysis supported the decision to reject age null 1, age null 2, but not age null 3. Let's see. Age null 1, is that engineering is equal to physical science? False. We reject that. We reject that engineering is equal, the median salary is equal to the median salary of computer and mathematics. Reject that. And we do not reject age 3 because there was no difference between physical science and computer and mathematics. So we can go to interpretation. And in interpretation, we say that data provides evidence that the median salary of recent graduates majored in engineering, physical science, and computer and mathematics differ. In particular, the median yearly salary of engineering graduates, which varies from 52,000 to 62,342 with 95% confidence, is higher than the salary of physical science majors and computer and mathematics majors. The salary of physical science majors range from 39,000 to 45,764. We should say the median salary, right? Because it's the 5th percentile that we're dealing with. And the median salary of computer and mathematics majors range from 36,000 to 775 to 47,004, also with 95% confidence. There is no difference in salary between the latter two categories. So this is basically what your cousin needs to know that the data provides her with, right? So what would you tell your cousin? So one thing you should tell your cousin is that if your goal is to select a major based on the median salary earned by new graduates, then you should go for an engineering major instead of going for physical and computer science. So remember, the cousin likes physical and computer science, but she's putting as first constraint how much money she makes with that major. She's likely to make with the major she chooses, based on the fact that her primary constraint is how much money she'll get. She'll be more likely to get a higher salary if she went for engineering versus mathematics and physical science. It's just kind of chances at play. The only thing that mattered was the major she picked for the salary she will make. All right, so again, now we're ready to go to problem 2. Here is what we're facing. Cousin was not satisfied with that answer. She thought she's not too ready to give up her passion just for money just yet. She was critical about your response. She thought, median salary might not be a good way to look into it. She said, since I am really passionate about physical science or computer science and mathematics, I'm likely to be at the top of my field. So she basically told you, I want to look at top salaries and see if those top salaries are different across the major categories. So your job is to help her compare top salaries among the same 3 majors. And for that, instead of looking at P5th percentile, the 5th percentile salary, we're going to look at the 75th percentile salary, which is the top salaries in the fields. What I suggest before you watch me going through things, you should go through the guided activity until you get to question 11, I think. To catch question 11, and try to solve the questions yourself by pretty much applying what we've just done up there to this new variable. That's the only change that will happen. And then you can come back if you have questions and watch the video where I take you through the steps themselves. All right, because it will be exactly the same as before. Okay, talk to you soon. Bye-bye.